Our last theorem is called the divergence theorem, or frequently Gauss's divergence theorem. While Green's theorem and Stokes' theorem involved curves surrounding some sort of two-dimensional surface or area, the divergence theorem is instead going to involve a surface surrounding a three-dimensional solid. Recall back in section 16.5, after we introduced the divergence, we showed that Green's theorem can be written as this, where we have the line integral over some curve C of f dotted with d with n, the n being the normal that points outwards. So if we draw a picture of this, here's our C going around region D. It's going in a positive orientation, and the normal vector points perpendicular to the curve away from D. And if you do that, then that line integral turns out to be just the integral over of the divergence of our vector field over the inside, over D. It turns out this equation is essentially true if we move up a dimension. So here, instead of looking at some area D, we have some solid in three-dimensional space. We're going to refer to that solid as E, and it has a boundary surface of S. We still look at the normal that points outward. We called that normal the positive orientation for the surface back in when we started talking about orientations back in 16.7. But basically, the divergence theorem says that the surface integral of some vector field over the surface, remember that surface integral is really just the integral of f dotted with the normal to that surface, and then the scalar surface integral of that. So essentially what we had here. And that's going to equal the triple integral of the divergence of f over E itself, over the inside. Now they've actually stated here that this is for a simple solid. Actually, this is definitely true for a much more general thing, but a simple solid is one that can be made type 1, 2, or 3. We're going to prove it for those simple solids, but just be aware that this is actually true in much more generality. In fact, the main thing is that the boundary, the surface boundary of S, needs to actually be smooth enough for it to actually work. It needs to be piecewise smooth. That's pretty much the main thing that we would be worried about. But other than that, we're essentially just relating the surface integral of a function over some boundary to the triple integral of the divergence on the inside. So let's go ahead and get started proving this. So first of all, we're going to let f be pi plus qj plus rk, like we normally do. Of course, then remember what the divergence is. We haven't looked at the divergence for a few sections, but remember the divergence just takes the derivatives of each of the components with respect to the exact same variable those components are for. So p is the x component, so we take the derivative of p with respect to x. We're not making it a vector. We're just literally going to add it to the derivative of q with respect to y, and the derivative of r with respect to z. So divergence is a lot easier to compute than the curl is. It's because we don't have to remember which of the orders that we put all the derivatives in. It's really just take the most obvious derivatives and add them together. Once we do that, we can actually split up our integrals pretty easily. So if we look at the triple integral over E of the divergence of f dv, since the divergence has three parts to it, we can actually split this up over that. Quite a bit of writing in here. We can also do the same thing with our surface integral. So we're taking the integral over s of f dot ds. Keep in mind there that f is our vector up here. The dot product can actually be split up over those, so we actually get the integral over s of pi, the first component of f, dotted with ds, and the integral of over s of qj, dotted with ds, and the integral of rk, dotted with ds. And what we're going to show that as long as we have our simple region that can actually be treated as a type 1, 2, or 3, then each of these integrals, all these three integrals, can be essentially just paired up. The integral of p over p of pi over s can be is equal to the derivative of the integral of the derivative of p with respect to x over the inside. Same thing here, these two are equal, and these two will also be equal. Since we are assuming that E is simple, we can treat E as a type 1 region. Remember what that means? That means E is the set of all points x, y, z, where x and y are in some region D in the xy plane, and z is between two functions of x and y. For type 2, it'd be kind of the same way, except the x would be between two functions of y and z, and for type 3, y would be between two functions of x and z. But if we treat it as a type 1, that will actually help us a lot with the r integrals, the ones that basically come down to the z component. And since z is between two functions x and y, that'll work out really nicely for r. For type 2, that will work out very nicely for x because x is the one between two functions. And for type 3, that will work out very nicely for q because y is between two different functions. So if we look at the triple integral over e of the derivative, I need that derivative in there. That's the integral. So the first two variables, x and y, are over d. So we'll do a double integral over d. And then we'll have an integral where we have our boundary for z. We're still looking at the derivative of r with respect to z. But now we're integrating that over z first, which is going to work out very nicely for our derivative here. And we have dA corresponding to the x and y from our d. Of course, the integral of a derivative is just going to be that function. So this is just going to turn into r, evaluated from u1 of xy to u2 of xy. So we'll just write it that way. So r of xyz instead is going to be xy u2 of xy. Then minus r of xy u1 of xy. Alright, so we've actually simplified our triple integral already. Let's take a look at the other side of this, look at the surface and surface integral, and show that we can get the same formula. So we kind of been doing this where we work our way to the same thing from both sides. We've done that on a few proofs already. We're going to do that here as well. So we're going to look at the surface integral of rk dotted with ds. Now we need to actually figure out what's happening with that surface. So keep in mind we are still looking at this as a type 1. So we have some region down here in the plane. This is our D. Above that, we have two surfaces. We have the one given by u1 of xy. We have another surface up here. This is given by u2 of xy. And then we have a vertical surface that is just basically over the boundary of D. We're going to give these names. We're going to call this surface on the bottom S1. We're going to call the surface on top S2. And the vertical surface in the middle is S3. The surface integral over the entire thing, this is going to be the integral over S1 plus the integral over S2 plus the integral over S3. And we're going to figure out what all three of those are. The first one that we're going to work with, the easiest one, is actually going to be over S3, because what's happening here? All of our normals to S3, because this is vertical, this is actually vertical, they're all going to be horizontal. They're all parallel to that xy plane. But we're only integrating over RK. This actually is in the positive z direction. So the dot product of k with anything that is horizontal is 0. Those are perpendicular to each other. So that means that the integral over S3 of rk dot ds has to be 0. If you want a little bit more explanation for why that's true, we can actually just go ahead and write this out. So remember, surface integrals are just the integral of whatever whatever vector field we have in here, dotted with the normal to our surface, and the integral of that scalar function. So if the normal is perpendicular to k, then k dot n is 0, and so everything turns out to be 0. Moving on to R2, or not R2, S2. Well, on S2, this is our top surface. The normals here don't have to be vertical, but they are all upwards. We can't have downward ones because this has to actually be the graph of a function. And because we have that, because we can treat this as the graph of a function, we have a formula for the surface integral over a graph. So the surface integral over S, where S is given by the graph of a function g of x and y, is given as the double integral over the region in the plane of this function here. But what we have here, we just have rk. We do not have a p or q. We can treat those as 0. So that makes this a lot easier. That means that these first two terms are gone, and we just have this r here. So we can turn this into the double integral over d of r dA. Though, instead of writing r dA, let's go ahead and write this as r of xy u2 of xy dA. So basically, we're putting in the value of z in for the z value. The z value here is on u2 of xy. The one thing that we do have to pay attention to here is that this formula is specifically for use when we are using the upward normal for that surface. If we're looking at S1 now, if we move on to that one, the unit normal there is not going to be the upward one, because we need to have a positive orientation on the boundary. Remember, the positive orientation is the one that points outward. So that was horizontal for S3, it was upward for S2, but it's actually downward for S1. And so this formula would not be the correct one to use for S1. But we can actually fix that pretty easily. We just need to multiply by -1 to compensate. So we just have a negative, the integral over d, doing the exact same thing we did for S2. We have r of xy u1 of xy. And so we can go ahead and combine those all together. Actually, let's put that on another page. So here, this one is 0, so it'll go away. This one turns into the double integral over d of r of xy u2 of xy. Now we could just go ahead and close the integral right now if we wanted to, but this one is going to be an integral over d as well, so we could just kind of combine those integrals. This one was the integral of r of xy u1 of xy, but it was negative, so it's subtracted. But if we actually look at this, this is exactly what we had back here. This double integral here was the triple integral of the derivative of r with respect to z, which is exactly what we were trying to show. So as long as we're treating this as a type 1 integral, this surface integral turns fairly easily into this triple integral. If we instead do this as a type 2, then we can easily get, by the exact same process, the surface integral of pi dot ds is equal to the triple integral over e of the derivative of p with respect to x. And for type 3, that one works very nicely for q. And so if our region is all three types, we can easily put them together, just add them together. We go back to here. If this is equal to that, that's equal to that, and that's equal to that, then of course these two are equal, which is exactly what we wanted to prove. If we want to generalize this to non-simple regions, then we can essentially just take whatever region we're working with, divide it up into a bunch of simple regions, and we can actually show that the shared boundary, if we kind of, maybe we'll draw a picture of this. Let's say we have something like this, where we have a e. This whole thing is e, but we can actually split it into two pieces. So kind of cut it in half and have an e1, e2. We can actually do the divergence theorem over each piece separately, and this shared boundary in the middle here will actually cancel out when we're doing the surface integral, because the normal direction I have to choose for e1 would be to the right, but for e2 would be to the left, and those opposite orientations on that shared boundary will end up canceling each other out. So we did sort of the same thing with Green's theorem, where we're able to take a more complicated region D and split it into multiple regions that were actually easier to work with. With the divergence theorem, we can essentially do the same thing. But we're not really going to actually do any of that in any of our examples. That's just mainly just kind of justification of why we don't need to have a simple solid. We just have to have one that has a nice enough boundary. So now we have 5 big theorems about integrals. The Fundamental Theorem of Calculus is from Calc 1, but these other 4 are from Chapter 16. And the main point here, that all these theorems relate the integral over some the integral over some boundary. So here we have the integral of px, or p, you could say pi plus qj over c, the integral of f over c, the integral of f over s. Those are all the boundaries of our regions here. For the Fundamental Theorem of Calculus and for line integrals, the integral over the boundary, since the boundary just has the 2 points, is just going to be a difference between those the values at those 2 points. But since the integral is really just adding up stuff in the first place, it's really the same idea. And we relate that integral over the boundary to the integral of some sort of derivative of that function over the interior. So here, for the fundamental theorem of calculus, it's literally just the derivative. For the fundamental theorem of line integrals, that's the gradient. Green's theorem and Stokes' theorem, we're really just integrating the curl. The curl in Green's theorem just being the one for a two-dimensional vector field. And for the divergence theorem, that derivative is the divergence. But they're very, very similar in their structure. In fact, these are all special cases of a much more general theorem that works for any dimension, which is actually frequently referred to as Stokes' theorem as well. We can write that as the integral over the boundary. Remember, we use the... Let's do v here. So putting a partial symbol here, partial v would be the boundary of v. If we integrate something which we'll call omega over that boundary, it's the same thing as if we integrate over the interior of the derivative of that thing. Now, getting into this is way beyond what we can even mess with right now, and it actually involves something called differential forms. Here, this omega is a differential form of one dimension, and this is a differential form of another dimension that is the derivative of that differential form. But we're not getting anywhere close to those right now. The main thing I wanted to just point out to you is that these are all very similar in what their execution is. The specifics might be a little bit different, but the ideas behind all of it is exactly the same thing. Alright, so I'm going to stop this video here. We've gone through... All we really needed to go through was the divergence theorem itself. In the next video, we will get into some examples of using it and show how this simplifies a lot of work. Doing these surface integrals can be a little tedious sometimes, but integrating the divergence over the interior turns out to be a lot easier most of the time. So, we'll get into some of that.